Okay. Okay. It's a great pleasure to invite Professor Subir Sachdev. He's from Harvard University, and actually he's one of the most renowned condensed matter theorists today. In fact, he had his early education in India. Then he did his education in MIT and did his PhD in Harvard University. He was in Yale University for some time, and now he has moved to Harvard University. Professor Subir Sachdev has made several seminal contributions. Um, he works on strongly correlated system, and some of his contributions have, can I say that even rewrites or overturns some of the textbook materials which we read, especially in things like phase transitions and all, and Lando's theory of phase transition and things like that. He has made a very wonderful contribution, and he has even won a lot of recognition. He has got a Dirac Medal from ICTP, and I mean, he has also written some very wonderful textbooks on quantum phase transition. And in recent times, he's been working mostly, his work has a lot of connection to other completely diverse areas like black holes, which he'll be talking. And especially he's brought some of the developments in string theory like ADS-CFT correspondence to a condensed matter system, which has really brought entirely new light in this whole subject. So there is a kind of a cross-fertilization between different subjects, which pioneers like Wilson and others did. It's a kind of a thing, which he has really been doing, where the borders or the borderline, the walls between the different subjects are all sort of broken, like a Berlin Wall. And he's been one of the persons who has made that kind of a pioneering work in those kind of an area. And his contribution is just like that. And I'm very extremely, very sincerely from the depth of my heart, we all thank Professor Subir Sachdev for, agreeing to give a lecture today. And we hope that all the students will get inspired that, a person like him who studied in a KV school in India, in Bangalore, and then he has risen to a level of being most accomplished condensed matter theorists of the world today. I thank you and welcome Professor Subir Sachdev to address this gathering. Thank you.
Thank you, Professor Shivakumar. I trust you can hear me. Yeah, so it's thank you for the invitation. That's a great, and thank you for the very kind introduction. I especially appreciate your mentioning my KV school in Bangalore, which I remember very well. It was a very good experience, and it stood me good stead in my rest of my life. All right, so let me share the screen. Okay, so I hope you can all see my slide and the red circle. Okay, so I will give a general talk on in some sense, an applied quantum mechanics, applying quantum mechanics to study the phases of matter. And one of the remarkable things is that macroscopic phases, metals, semiconductors, insulators, all these different materials that you can hold in your hand, an understanding of their properties really requires application of quantum mechanics, something that was developed to understand a single hydrogen atom in the 1920s. And so this application of quantum mechanics has been a great success story. But it's still very much an ongoing story because there are new ways in which quantum mechanics is influencing the behavior of matter on microscopic scales. So I want to give you a flavor of that. I understand all of you have at least some exposure to quantum mechanics. Maybe have seen the Schrodinger equation and solved it for the hydrogen atom or something like that. I won't throw too many equations, but please feel free to ask questions, maybe in the chat. You can interrupt me, Dr. Shivakumar, if there's some urgent question in the chat, or later on after my talk. Okay, so here's my outline. I'll begin by just reviewing what I'll call the conventional phases of matter. So these would be phases of matter you would find in a textbook written, in the 1990s or early 2000s, where much progress has been made starting from 1930 onwards in understanding, the basic properties of many standard phases of matter. And the fundamental common thread here is that you can understand the properties of millions of electrons simply by extrapolating from the properties of a single electron. There isn't that much, it's not that different to do a theory of an atom to do a theory of a metal. So I'll talk about that, all the successes of this conventional point of view. But then I would say starting in the late 80s and continuing today, there's been a remarkable set of experimental discoveries and also many theoretical developments, which I'll try to give you a flavor of, where this 1, 2, 3 infinity point of view of metals doesn't work. That is, just understanding the property of 1 and 2 and 3 electrons is not sufficient, even conceptually, to tell you what happens when you have a million of them. Entirely new phenomena appear, sometimes called more is different by Phil Anderson. But there are new concepts like emergent gauge fields and topology and multi-particle entanglement and even emergent gravity that are being used. And I will try to give you some flavor of why we need these ideas. Okay, but let's begin in a much more simple setting, or the older setting first. So, so the first success really of quantum mechanics applied macroscopically would be, I would say, the Sommerfeld theory of metals. Metals, by metals, I mean one of these materials here. They have some basic properties. They're shiny, they conduct heat and electricity efficiently. And all of these properties can be understood from the basic fact that what happens in a metal is that the atoms, each atom loses a few electrons, 1 or 2 or 3. These are the outer shell electrons. And so while the inner shell remains localized near the nucleus of the atom, the outer shell electrons are delocalized through the entire crystal. They're moving through really all the way through the entire system. And this ability of electrons to delocalize and move freely helps explain these basic properties of metals. So a bit more detail. So since the electrons are moving freely through the crystal, you can put them approximately in plane wave states. Now the crystal is not, not just there is a potential which oscillates periodically as you go from point to point. And so you can account for this external potential from the ions by transforming from plane waves to block waves. Maybe you haven't heard about block waves. So all you really need to know is that when you have block waves, the range of momentum k is finite. It just goes from minus pi over the lattice spacing to pi over the lattice spacing. But other than that, they just pretty much look like plane waves. So here's the very simplest theory of metals. You find the dispersion, the energy levels as a function of k. It's some simple curve like this. And then just like you do for the hydrogen atom, you just fill up the states. You first fill up the lowest energy state, and then the next, and the next, and the next. And you fill it up with 10 to the 23 electrons up to what's called the Fermi energy. And the most fundamental property of a metal is that there is this Fermi energy, and you have to excite electrons for the metal to now do anything, to conduct electricity. You have to take an electron from below the Fermi level and put it above the Fermi level. And the key point is that since these states are so closely spaced, their spacing is roughly 1 over the size of the crystal. This energy is extremely small. I mean, it's greatly exaggerated in this plot. this is essentially zero energy. So you can have electrons go to an excited state with essentially zero energy, and then these can now move around and carry current. You could have more on this side than that side. These are the right moving electrons, these are left moving electrons. So there's a net current that can flow with essentially no energy cost. So as you've seen in all this discussion, I've just talked about each electron moving, just being excited one by one from occupied states to empty states. The only way the electrons feel each other is through the exclusion principle. That is, an electron can only move into a state that's not already occupied. But other than that, it's just a one particle theory, and that, now you can take a course of solid state physics and go into all kinds of details, but I just gave you the basic idea and really understand in precise quantitative detail the properties of many metals. Okay, so these electrons, as they're moving around, are not entirely independent. They will scatter off each other. And it's the scattering of the electrons that leads to a finite resistance. Otherwise, the resistance would be zero. So one fundamental quantity that people want to know about is, what is the scattering time? And if the scattering time is long enough, then you can argue that the electrons are basically independent, because for the longest time they're moving on their own, and then they scatter off some other electron and move in a different direction. So as long as that time is, long enough, then the idea of individual electrons moving on their own, which we sometimes call quasi-particles or quasi-electrons, because they're a little bit renormalized from a bare electron, that idea still holds. So you can ask, how long does this time have to be? And there's certain arguments based on something like the uncertainty principle that the time has to be longer than the Planckian time. So this is a fundamental time that you make out of Planck's constant and absolute temperature. And this is the only quantitative equation I'm going to use in my lecture today. This Planckian time. So just remember, this time is just made out of the absolute temperature, Planck's constant, and Boltzmann constant. So for the theory of the one electron standard theory of metals to be valid, the scattering time has to be longer than the Planckian time. Then what about insulators? Well, insulators are formed by just filling up all the electrons in any given band. So remember, there's a band here because of the periodic potential of the crystal. There's no more states over here. There are further states in a separate band, which are at much higher energy, which I haven't drawn. And so now, because every state is occupied, there's nothing the system can do when you apply an electric field. You can't, it required a lot of energy to move this electron to the upper band. Since that happens very rarely, the conductivity is basically zero. The resistance is infinite. And so you have this remarkable transition from zero resistance to infinite resistance when you go from a perfect metal to a perfect insulator, just by changing the density of electrons. And just this explanation, this simple fact that the resistance can go from zero to infinity very quickly was one of the first successes of quantum mechanics. There was no classical theory that could help explain that. Okay, so I have told you about metals and insulators, and the next step is to tell you a little bit about superconductors. So what happens in a superconductor is you start with a metal, say like aluminum, and what Bardeen, Cooper, and Schiffer realized, although they didn't phrase it in these terms, so what happens is that the electrons pair with each other. So these electrons all form a pair, and that pair is a boson and can undergo Bose-Einstein condensation. So, and when that pairs of electrons pair and form a Bose-Einstein condensate, loosely speaking, then you get a superconductor. So this is something that can conduct electricity without resistance, even in the presence of impurities. I mean, only a perfect metal has zero resistance at very low temperatures, but without impurities. But a superconductor, even with impurities, even at finite temperature, can have exactly zero resistance because of the existence of this Bose-Einstein condensate. So here there's something bit beyond just single electrons moving on their own. it's 2 electrons. The electrons go 2 by 2. So, all right, but that's still not that much different from the independent electron picture. It just went from 1 to 2. So one of the most famous superconductors are these high temperature superconductors discovered in 1987 when I was a postdoc. And and that really changed my career because I started working on them right away. And so these go superconducting at, say, liquid nitrogen temperature. Here's a little piece of it. And if you take that piece of it and put a liquid nitrogen, and then you put this over these magnets, one consequence of the zero resistance is that currents can easily flow in this crystal. And I'm sure heard about Lenz's law. So the currents will flow in a way to oppose the external magnetic field. And so actually, this opposition is perfect in a superconductor. So all the magnetic field is expelled from inside the superconductor. And so that, that costs some energy to do that. And that's why the superconductor floats above, has this magnet because of the expulsion of the magnetic field. Of course, at that point, it's become it's warmed up to above liquid nitrogen, and therefore didn't do that anymore. Okay. All right. So that's my 15-minute summary of solid state physics 101, something that will be taught over a whole semester. In fact, I did teach such a course in the last semester at Harvard, and all my lectures on YouTube if you want to go to take a look at it. But the basic idea to summarize is that there are many phases of matter: metals, insulators. Semiconductors are basically insulators with a small band gap. And you can understand remarkably well all of their observable properties by just applying by simple extrapolation in the end of the one electron theory of the hydrogen atom. And this has been, of course, of great importance. All these, the development of transistors, lasers, and everything that goes into your iPhone was built on this application of quantum physics. I mean, so it's really an amazing success. Okay, so now I want to come to the 21st century and talk about new materials that people have been discovering in the lab. In fact, even I lied a little bit. The superconductor I showed you, yttrium barium copper oxide, is really part of the new materials. The fact that it's a superconductor and the nature of superconductivity is, was pretty much along the lines of Buddy and Cooper and Schrieffer, but everything else about it really involves these new concepts that I'll talk about in parts 2 and 3. So one of the emerging trends in condensed matter physics has been the role of topology in different ways, and how that becomes a tool for understanding better the many electron physics. And the new phenomenon that really want to talk about now in its very basics is the phenomenon of entanglement. That's not something I've mentioned yet. Entanglement is really the key ingredient from all the new things I'll talk about. So the idea of entanglement, or the phrase entanglement, I'm not sure who came up with it, but the fact that entanglement is a very strange feature of quantum mechanics, was pointed out by Einstein, Podolsky, and Rosen in 1935. Maybe I'll say a little bit about, I should have put it here. Yeah, so I had some slides which are not coming up, but I'll say it in words. So entanglement, I'll say it in a few minutes. I do have a picture that I can use. All right, so one place where people are now understanding that entanglement plays a role in the properties of a big material is in materials called Mott insulators. So what is a Mott insulator? Well, a Mott insulator is different from the kind of insulator I told you about earlier, which was a band insulator, because it's precisely the Coulomb repulsion that makes it an insulator. You know, what I said before was for an insulator, you just occupy all the states. And so it's not the actual repulsion between the electrons that's keeping them apart. It's just that they have nowhere to go. All the rooms are full. There's no place to move. Okay, but now imagine an insulator like this. So each arrow represents one electron, and which is sitting on some atom, and the atom happens to be on the vertices of a triangular lattice. Now each atom or each room can have 2 electrons, just like the 1s level of hydrogen can have a spin up and a spin down electron that makes helium. So each room can have 2 electrons, and that's what band theory would say. So band theory would say if you put in 2 electrons on each on each atom, you'll get an insulator because all the rooms are full. But in a modern insulator, the room's only half full. You put 1 electron in each room with its spin, which can point in different direction. I'll come to that in a minute. But that electron doesn't want a partner in the same room because they repel each other. So it's the Coulomb repulsion that prevents the electrons from moving, not the exclusion principle. And that's what a modern insulator is, where the Coulomb repulsion forms this half-filled state which cannot conduct electricity. But once you have this half-filled state, the story is not over, because now the electrons also have to decide what to do with their spin. They can point in, up or down or any other direction. There's a qubit or a 2-state quantum system at each atom. And so what we know is that there's an interaction between the electrons, the spin-dot-spin interaction, which perhaps you've seen in your quantum course, between any pair of nearest neighbor electrons, which wants to orient them in opposite direction. So if one electron is up, the other one wants to be down. Now, it's not as simple as that, because if this was up and this was down, then this electron doesn't know which way to point, because it wants to be opposite this one, so it should be down. It wants to be opposite this one, it should be up. So what do? Well, they make a compromise. If these were classical spins, which wanted to minimize this function, they would form this pattern, the 3 sublattice pattern, where they point at 120 degrees to each other. So this is sometimes called non-collinear Néel order, and there's many materials that you can see in the lab and see that they actually do this, that the electrons are forming this pattern of their spins. Okay, so this is quite a non-trivial thing, but it's still sort of a classical view of electrons, because the quantum state is still a product of the individual wave function of each electron. So you take the electron pointing here times electron pointing here, and so on and so forth. The many-body state is a product of the single particle states. Okay, so now the question is, can you get, what's going on here? Can you get some, why do I have 3 copies of this? Okay, oops, sorry. Yeah, okay. Can you get a state which is intrinsically quantum? And this kind of state was proposed by Anderson in the 1970s, now called the resonating valence bond state. Actually, this state was proposed even earlier by Pauling, but not in exactly the right context in the 1940s. And the basic ideas goes back to really the structure of benzene by Kekulé. So but let me describe it in the context of this triangular lattice model. So if you take 2 electrons, take this pair of electrons, if only the 2 of them existed, then the lowest energy state for a pair of spin 1/2 electrons is the so-called spin singlet pair. It's an entangled pair, where if the first electron is up, the second one is down, but it's a superposition of that state with the opposite orientation. So this is the basic structure that forms the entangled state. And what Einstein, Podolsky, and Rosen pointed out in 1935 was, a thought experiment, where imagine you could separate these 2 electrons without disturbing their spin. then quantum mechanics says is that they're still entangled, no matter how far apart they are. And the electron in your hand, if you have the first one, is still entangled with the electron in my hand. But neither is up nor down. However, if I look at my electron and I see it's up, then your electron must be down, and vice versa. So there seems to be this action at a distance effect, which my measurement influences your observation instantaneously at the other end of the Earth. And this is what Einstein thought was a bug in quantum mechanics, and felt that there must really be some correction to this. What we know today that it's not a bug, but actually the most interesting feature of quantum mechanics. It is true; it's been tested in many experiments, and I think philosophically the way you get to terms with it is that the idea of action at a distance is not quite correct. The new idea you have to accept is that that a quantum state is not a local object. When I have this electron, you have that electron, we sharing the same state. And that state is an abstract state describing the state of the universe. It's neither here nor there. So it's not as if anything's going from me to you when I'm looking at that state. We're sharing the same state. Okay, so that's an entanglement of a pair of electrons. Then what Kekulé did when it is in the theory of benzene was take an entanglement of 6 electrons around a hexagonal ring. They each form these valence bond, as you would call them, but they could resonate between 2 possible configurations. I should have had a picture of that. So here, in the Pauling wave function, the resonance is not between 2 possible wave functions. The resonance is between an infinite number of possibilities equal to the number of ways you can pack dimers on the triangle lattice. So the actual wave function written here is a superposition of many configurations. Here D refers to a dimer covering up the lattice. So here's one dimer covering, but here's another, let's see, here's another one, here's another one, and so on. So you can see there's many resonance possibilities when you resonate things around a rhombus there, just like you have resonance in benzene in the 2 configurations. But this is now far more complicated, because what's happening as a result of the resonance is that all the electrons are getting entangled with each other. Initially there's only a pair of them. Then when you resonate, okay, there's 4 of them and 6 of them and so on. So in the end, there's a new state of matter whose reason for existence is in fact resonance. So it's something completely different that you could not understand with a 1 electron picture. And it has, remarkable sorts of new properties, which are a direct consequence of this entanglement. And so what we need is a new language to talk about this entanglement and new equations to describe these collective properties. It's hopeless to try to solve the underlying Schrodinger equation for each electron. That's way too complicated. And so we have to work with what are sometimes called emergent degrees of freedom. Okay, so that's the famous RBB state of Anderson. What we did in these papers was come up with an actual theory of such a state and describe its really some of the remarkable consequences of this long-range entanglement. And the way we did it was to start from this familiar state and study a quantum phase transition into where you imagine tuning some parameter, like a second neighbor exchange or something. And by studying this transition, we could then come up with a theory of what's going on this side. And so this state, often called the Z2 spin liquid, and I'll try to give you some indication of what that Z2 means, has a certain emergent excitations, new types of objects that people are now seeing some indication of in experiments. And later on, there was also this very beautiful exact solution of a very different model by Kitaev called the toric code, which has the same set of excitations. So let me tell you about some of the remarkable things that happened because of this long-range entanglement. So one of the first is the property of fractionalization. Okay, so an electron in an ordinary metal carries charge E minus E. Okay, let me not worry about the sign. Electron carries charge E and spin a half. Now, when electrons form, Cooper pairs, they pair up in a superconductor, then you get two electrons. So the object will have charge 2E, and in principle, it could have spin 0 or spin 1. And so on. You can pair up electrons in different ways. And so when you do that, what you find then is that if you have any collection of electrons with an odd charge, either 1, 3, 5, -1, -3, then its spin must be half integer. It has to be 1/2, 3/2, 5/2. That's the only possibility when you just use the rules of additional angular momentum. On the other hand, if you have an even number of electrons, then the spin must be an integer, 0, 1, 2, 3, and so on. And that's just a basic property of any state you would write down in the textbook theory of solid state physics, that integer charges are tied up with integer spin. Even integer charges are tied up with integer spin, and odd integer charges are tied up with half integer spin. However, this RVB state violates this rule. It can have an excitation that has charge 0, which is even, but spin a half. And what is that excitation? It's sometimes called the spin-on. And here it is. So you have this liquid of these valence bonds resonating, but then you have this lonely particle here, which is an electron, which is not paired with anybody. So this is not part of the ground state. It's some excitation. And now this excitation can move around. And as it's moving, you see what is it doing? There's no charge that's actually moving, because every room still has exactly 1 electron. So the charge in any room is always just 1. Nothing has moved. But the spin is moving, because these electrons are paired in spin 0, spin 0. The spin is moving, and it's spin a half. So now you have violated this one very fundamental rule that an even integer charge, in this case 0, cannot have a half integer spin. In fact, it can. And so this property is called fractionalization. And this is the fractionalized spin a half excitation, which can exist in this long range entangled state. Okay. And one other important property of it is that if you can't create one of these particles, the only way you get, if you hit the system with something with your laser, it'll break a bond, and that bond will create 2 of them. And then the spin-ons can move apart from each other and go up to infinity. So there's another spin-on somewhere else out at infinity, which was created when you created one of these. So this is a particle, this fractionalized particle cannot be created by any local operator. And that's what's an amazing property of it, but it's still there. Okay. All right, so that's a spin-on. And you can detect it experimentally by various approaches. There's even more subtle excitation, sometimes called a Vison or an M particle, depending on how you're thinking about it. And this Vison is a spin 0 excitation and also charge 0. It's something rather new, but it's kind of analogous to a vortex in a superconductor, if you know about that. So what is a Vison? Well, you take the ground state wave function. Remember the ground state, the ground state was this wave function here. You take this wave function, which is some superposition of dimers with some phase factor CD next to it. And then all you do is you put a -1 in front of some terms. Okay, so what did I do? That's a spin-on, and here's a Vison. So I put a -1 in front of some of the terms, some dimer coverings. And how do I decide put a -1? Well, what I have to count this integer ND. What is ND? What is ND is the number of dimers crossing this red dashed line. You just pick a point. That's where the Vison is sitting. and you make a line going out to infinity. Any line. In fact, it doesn't matter which line. And then if you have a dimer crossing this line, here ND is 1. For this configuration of dimers, you put a -1. Then you keep going. Here's another one. There's only one dimer crossing this line. Here's another one. Only one dimer crossing the line. Here's 2 dimers crossing the line. There's one here and one here, and that you put up. You don't change the sign there, and so on. Okay, so now by looking at the properties of this state, you can, it's not that difficult to see some basic properties just by looking at overlaps of this state with other states and so on. First of all, the position of the line doesn't matter. And you can put it anywhere, you get essentially the same state. And moreover, all these -1s here don't really cost you any energy. For example, here, whether you had the -1 there or the -1 there doesn't make much of a difference, because in the end, the only thing that matters when you compute anything is the net flux, the total number of -1s around that loop. And so this has a flavor of what's called a Z2 gauge theory, if you've heard of that thing, but don't worry about it, you haven't. So the only place the -1s matter are just around here. So this is the only place there's some any energy cost. And so it's a very small amount of cost, some finite but small cost. And so there's some excitation which is only sitting here. You can't do any measurement to measure this line. The line is just a figment of your imagination. It's sort of like a gauge choice in electrodynamics. And that also indicates why this thing is described by emergent gauge fields, which I won't go into here. Okay, so this is some ephemeral excitation which has neither spin nor charge but carries energy, sort of like dark matter. But it has to exist in a Z2 spin liquid. And very much tied to the existence of this long-range entanglement of the dimers. Okay, so from these, now you can do all kinds of bizarre things. And I have in fact taught a whole course on these things, but I want to move on. But so among other things you can see quite easily is now what happens when you have 2 of these excitations. Okay, so what happens if you have a spin-on and a Vison? Well, if you move the spin-on around now, when it crosses the line, it will pick up a -1. So you have this strange thing that when a spin-on goes around a Vison, it picks up a -1 phase factor. So this is similar to when 2 fermions exchange, you get a -1. Here, you have 2 different types of particles. One is a boson, the other could be either a boson or a fermion, and when one goes around the other, it picks up a -1. So these types of particles with different statistics other than the conventional boson Fermi statistics, which can even be distinguishable, are sometimes called anions. So this very simple state of Anderson is known to have, and proven to have now these anion excitations. You have these spin-ons and Visons, and in fact, the spin-on can be either a fermion or a boson. There's 2 types of spin-ons. And it's sometimes written these complicated fusion rules or described by some complicated gauge theory. And all of these properties were found exact realization in Kitaev's famous toric code. So what about topology? So what is this connection with topology? Now imagine taking all those electrons and putting them on a torus. So of course, in the real world, that's very hard to do. But as a thought experiment, let's imagine doing that. So the state I wrote down, seemed like a perfect, resonating valence bond state was a unique state essentially with some phase factor CD chosen. But now when I put it on a torus, I can take this infamous branch cut that I was showing you here, this branch cut, and make it go around the loop of the torus. That's the same branch cut going around this way. But notice now this branch cut doesn't end anywhere. It's a continuous, never-ending loop. And I told you the line itself is unobservable, costs no energy. So amazingly, you can now make another state, which you can show is orthogonal to the original state, which has essentially the same energy. So you get additional states on a torus. You get new degeneracies on the torus that you don't get on the infinite plane. And that's sometimes called topological order. That somehow the quantum mechanics, the fact that there's entanglement across the entire system, means that the system knows whether you put it on a torus on a plane. It could be infinitely large system. It doesn't matter how big it is, but somehow it seems to know that whether it's sitting on a torus or whether it's sitting in the plane, because the spectrum changes. And this is something you'd never find in any of the conventional phases. So this is one of the simplest examples of what's called topological order. And so let me give you another picture of it. So here, just try to take a little piece of the torus. And here's my branch cut with 4 lines, 4 bonds crossing it. And now I'd look at all different configurations and do all possible local rearrangements of these valence bonds. So I keep count of how many bonds are crossing the red line. And what you see now, it's 2, it's 0, 2, and so on. What you'll find, no matter what you do, as long as it's a very local rearrangement, reasonably local, much that it's always an even number. Nothing you can do changes the number of bonds crossing this never-ending line by an odd number. In fact, you can do a very non-local arrangement. If this was a torus, I go around this vertical loop of the torus, and I make a complicated rearrangement along that loop, then you can change it. So what you see there's a very simple illustration that you get a 4-fold degeneracy, depending on the 2 cycles of the torus. There's one state with an even number of bonds crossing this line. There's another state with an odd number of bonds crossing this line. They can't be any different from each other because locally they look exactly the same. They only differ in this very global quantity that has you go all the way around. So there's essentially no negligible energy difference between these 2 states. Okay, so that's an elementary introduction to some new ideas that came up in the early 90s. And which have had a huge impact, especially in the theory of the fractional quantum Hall effect. In fact, some of these ideas came up earlier in that context. And the theory of spin systems and some applications to experiments. But I would say the cleanest applications to experiments so far is in a very recent paper by my colleague Misha Lukin's group at Harvard. So I'll just give you a little flavor of what you have to do to start detecting these states with long-range entanglement. But there are many other experiments in many different systems, even in condensed matter systems, with varying degrees of confirmation of some of these ideas that I mentioned. So in this particular set of experiments, they're not strictly speaking in matter. They are artificial matter or synthetic matter, sometimes it's called. So what you have is a bunch of laser tweezers. So this is some laser beam that has a very tight focus. And each such tweezer has one atom, let's say rubidium, trapped in it. So this is rubidium in its ground state. And then you send in another set of lasers, which excite this atom, the outermost electron of rubidium, to a very big orbit. Principal quantum number n equals 70 or something like that. Okay. Now, so when the atom is really tiny, so that's the state G. So that this is the ground state G. That's the state G here. This is the excited state or the Rydberg state called R. And this is the laser beam. Omega is the so-called Rabi frequency, which takes an atom in the state G to state R, and also vice versa, takes an atom in state R to state G. This is, stimulated absorption and stimulated emission. Okay, but the laser beam is so strong that we don't worry about the spontaneous processes to other states. All right, now the laser beam is not exactly on resonance. It differs, that is the energy difference between this state and this state, is some very large energy. and then the electron volts, and then the laser beam also comes up to those electron volts. But there's a tiny difference, and that difference is called the detuning, which is delta. So in the so-called rotating reference frame of the laser beam, the difference in energy between the Rydberg state and the ground state is the small number delta. So this, with delta is positive, then the Rydberg state, then the laser beam has a higher energy, then the Rydberg state effectively moves up to, sorry, other way around. If the delta is positive, then the Rydberg state is below the, which way is it? Okay, yeah, sorry. The laser beam takes the ground state above the Rydberg state, yeah, if its frequency is high, and that puts the Rydberg state at lower energy, so that's delta is positive. All right, so that's for a single atom. This is the Hamiltonian write down for a single atom in the presence of this laser. But now you have many, many atoms, many different tweezers next to each other. So this is like a single two-level system or a qubit, which you can control to great precision. But now you have many of these two-level systems sitting around. And the beautiful thing about these experiments is that these atoms start to feel each other. And the reason they feel each other is because this Rydberg state is so big. Now, if one atom is in the Rydberg state and the other in the ground state, you can just forget about, they don't feel each other at all. If they're both in the ground state, they don't feel each other. But if they're both in the big state, which is not shown here, then there's an extra energy cost, V of I minus J, depends on how far apart they are. This is atom at site I and atom at site J. And so this is a very huge energy, and it falls off rapidly, but it's huge. So there's what's so-called a blockade effect, that if you excite this atom into its Rydberg state, because this energy is so large, then its neighbors don't want to be excited, because if they got excited, they would feel the repulsive energy of this this excited electron. So this blockade now builds quantum entanglement. This is what you need. You need the behavior of one electron to the one atom here to be influenced by the behavior of the other atom, just like the Mott, the Mott repulsion. So there's a blockade here, and the moment you have blockade, then all kinds of interesting entanglement can happen. So there've been many experiments on this. One just came out in Nature, which I'll show you. And this is the theory that was done earlier by primarily by my current student, Ryan Samajhdar, on the square lattice. So you take the Rydberg atoms, put them on a square lattice. You take this Hamiltonian and run it through a computer and ask, what are the atoms going to do? And on the square lattice, they form, classical, conventional states, effectively. Just like this antiferromagnet I showed you, where they form this 120-degree pattern. Here, the patterns are rather more complicated. You get checkerboard patterns. So every, I think, yellow square is where the atom is in the Rydberg state, and here is in the ground state. So the atoms alternate because the nearest neighbor atoms repel each other if they're both excited. So every second one of them gets excited, and you get this checkerboard pattern, which is very similar to this antiferromagnet. But you can get all kinds of other patterns with different symmetries as you change the range of the interactions and the detuning and so on. So, so there's a very intricate phase diagram that came out of Ryan's study. And remarkably, the experiments are done. This is the paper just published in Nature with 256 atoms in a square lattice, individually controlled, so 256 tweezers. And here's a picture of the checkerboard state and some of the other states. In fact, it's all in amazing agreement with the theoretical predictions. We've also studied some quantum phase transitions, which has turned out to be also worked out very well. Okay, but that's really, all of this is largely part of the part one. These are conventional phases with, the final wave function can simply be understood by a product of single particle wave function. Can you find anything which has entanglement? Well, so now that's still work in progress, but there's been some very exciting developments. You have to take these tweezers and put them not on the square lattice, but on a Kagame lattice. And then what Ryan discovered was that on the Kagame lattice, again, there were these conventional phases, the nematic and the staggered with different patterns. But there seemed to be this window of here where it seemed very likely that there was some kind of resonating valence bond state. So that's not been confirmed for this particular lattice, but there was a proposal by Ashwin Vishwanath and Ruben Verison of using a slightly different lattice, which turns out to work very much better. So now these are, atoms on the links of a Kagame lattice. So each one of them is a laser tweezer. It's a picture of it. And then you can tell, you just look at this picture and you can tell which atom is in the excited state and which is in the ground state. And then here's a picture of the atoms in the excited states. And each atom in the excited state, you draw an ellipse on it. And now you see the valence bonds. You can think of the atom in the excited state as a valence bond. And this is the particular picture you see. Then you look at it again a bit later and you see a different picture. You look at it again, do the experiment again, you see a different picture. So, and you can't predict which one you're going to see. So a natural prediction is that your wave function is the sum of all of these. In fact, precisely the RBB state that I was telling you about earlier. And there are some experimental indications that's indeed what's going on. I don't have time to talk about that. Okay, so there I've given you some idea of these new ideas on long-range entanglement and fractionalization and anions and even experiments that are starting to just detect these very remarkable consequences of long-range entanglement. Of course, another place where people are very much interested in exploiting entanglement is in quantum computers. That also you can view as some kind of complicated many-body state. But I think that's a much harder task than doing what we call here quantum simulation, which is simulating some many-body simple Hamiltonian. What we require for quantum computers is not just to control the state of each atom, which you can do now, but also control the interaction between any pair of atoms. And that's not something you can control here. That's except by moving the atoms around. But once you move them around, then okay, that brings its own different set of complications. But that's presumably the future that these experiments are going to go towards. Okay, well, I'm almost running out of time, it seems, so I won't really have time to really go into this other than say a few things somewhat quickly. If you have questions, I can come back to part 3. So there's another class of systems which also have entanglement, but entanglement which is rather different because it doesn't have these very clear-cut anion particles as emerging as excitations. In fact, it doesn't have any particles. So these are sometimes, that's why these are systems without particles or strange metals. And okay, so and that's turning out to be these systems of quantum mechanics entanglement, which have no particle-like excitations, are turning out to be crucial to understanding what are called strange metals, and also amazingly to understanding what happens to quantum mechanics near black holes. That's a huge field these days. Okay, so the simplest place, at least the first place I met the strange metal, and I've been still thinking about them since then, is again in this famous high temperature superconductor. And I showed you this how it goes superconducting in that little experiment. Here is the more global phase diagram, where as a function of the electron density and temperature, you get the superconductor. So the experiment I showed you was down here. But if you raise the temperature, which is still pretty low, this is 200 Kelvin, the system looks like a metal. But if you look at the details of it, it doesn't really look like a metal. And that's why it's called a strange metal. Why doesn't, so now I want to recall the one fundamental fact I stated about a metal in the very beginning, that the quasi-particles in a metal the collision time between electrons in a metal must be a time much greater than this Planckian time, h bar over kT. Well, if you look at this strange metal and measure this time, and I won't go into how you measure it, you find it's not much greater than h bar over kT. In fact, it's almost exactly equal to h bar over kT. This number alpha is over here. It's pretty close to 1 across many of these strange metals. So this is a very strange beast where the electrons are getting entangled with each other in such a complicated way that the actual excitations are not even particles. We found the E particle and the M particle, and the Vison and the spin-on in the spin liquid. Here, there are no particles. So how do you talk about such a state? And so that's been a major, major effort, certainly by me and by many others. And we don't have a completely satisfactory theory to describe these experiments. So in this particular class of materials, I would say that experiments is ahead of theory. There are many more experiments than any complete theoretical understanding. But I think a lot of progress has been made using a model, and I'll just describe this model called the Syk model. So this is model in one form was proposed actually by me and my graduate student Jinwoo Ye in 1993 or late 92. And Kitaev came up with a much, a simpler version of it with the same properties. Okay, and also understood many things in a much deeper way. Okay, so what's the fundamental property of this? Well, one of the basic properties of this, it turns out, is that the entanglement has a scale invariant structure. So very loosely speaking, I showed you the way you build up entanglement in the spin liquid was the electrons form singlets, valence bonds, and the valence bonds started resonating. So there was a fundamental scale there, which is just the size of a valence bond. It could be 1 or 2 or 3 lattice spacing, but not too large. And so the entanglement between at least electrons, the fundamental entanglement was over a certain distance. And then there was this subtle topological long-range entanglement. Here, that's not what happens. There's entanglement of the same type at all scales and all distance scale. And that's what prevents them in some ways of having any quasi-particle excitations. So I'll describe a simple model which is solvable, which has this rather bizarre type of entanglement. And we strongly believe that strange metals have a very similar type of entanglement. But this simple model turns out to have an alternative description. And this is the idea of duality. When you're describing a quantum system, there's no obvious set of coordinates to describe it. Describing a particle uses position and velocity. Quantum systems, they can be are intrinsically non-local, and they can be new variables or dual variables to talk about the same thing. The one example of it is, when you write on the Schrodinger equation, you can write on Schrodinger equation either position space or momentum space. And there's a position space wave function and a momentum space wave function. They look very different, but they're talking about the same thing. Exactly that here, there are more complicated dual variables for the Syk model, which in fact, and the dual theory turns out to be a version of Einstein's theory of general relativity, amazingly, and near a black hole. Okay, and the fact that this could happen was something I suggested back in 2010, and now it's been proven through some very brilliant analysis by Kitaev and Maldacena and Stanford. Okay, so let me just, out of time, let me just describe the model anyway. And it's very easy to describe. I won't really have time to tell you anything about the duality, but I can answer a few questions if you wish. So the Syk model works this way. So you take a bunch of sites, put them at anywhere, doesn't matter. And then you occupy a few of them by electrons. So here I'm just looking at the charge of the electron, not drawing the spin. So these purple dots are where the electrons are. Now these electrons can move around. There's some tunneling matrix element. And what you say is that the electrons can only move in pairs. And that will really force them to entangle. So this is kind of a at least in the Syk model, it's sort of an arbitrary fiat. It's a thought experiment, if you wish. There are more realistic models which you could hope to see in experiments, but they are more difficult to describe, so I won't do it that way, but have the same properties. So if you take this particular model, which is easy to describe, but a little bit unphysical, you allow the electrons to only move in pairs. So there's some certain quantum mechanical amplitude for, say, this pair of electrons to tunnel to this pair of sites. Of course, the electrons are identical, so it could be either way. You can't tell which electron's going where. And so there's a certain amplitude whose square is the probability that this pair of electrons will go there. And then there's a different amplitude that these two pairs, will go there, and so on. So any pair is connected to any set of empty sites. So anything that's possible will happen. Now, to fully describe the quantum system, I have to tell you the amplitude of each of these, and then you have to build up the wave function by solving the Schrodinger equation with all these tunneling processes. That's impossible to do, even on the world's best computers. But what we showed was that if you allowed each of these amplitude to be an independent random number, that's really all you need to do. You just choose some set of independent random numbers. Then this goes from being a problem you can't solve on the world's best computers to a problem you can solve easily in a few seconds on a laptop, just by allowing these amplitudes to all be uncorrelated random numbers. And that turns out to give a state with this scale invariant entanglement. And also, if you measure the analog of the scattering time, which is this Planckian time, exactly as seen in experiments, and also this duality to black holes, which I've already mentioned. But I think I'm out of time, so I'll stop here. I have a few more slides about black holes. Happy to, address questions on that, but I think I'll stop here. So thank you very much.
Thank you. Thank you, Professor Sweet. Thanks a lot for a very, very exciting excursion in this condensed matter, the newly discovered metals. Hello, can you hear me?
Yes, I can hear you.
Yeah. Hey, see, now, are there any questions? I mean, there are some questions in the chat. Now, those who asked some questions in the chat, can you please?
Yeah, so let me go down the chat. So one question is, how are mod insulators made? Is doping a possible method for this purpose? Yeah, so how are mod insulators made? Well, that's a question for solid state chemists. I mean, so I think for example, Professor C.N.R. Rao has made many mod insulators in his lab in ISC Bangalore. In fact, he made very early on this parent material of the high temperature superconductor. So for example, if you take, what am I doing? Sorry, I stopped share again. Excuse me. Yeah. Oh, there we go. Okay. I have to go through the whole thing. Well, it's good to see all the slides again. Jog your memory. Oh gosh, that's the trouble with all this animation. Yeah, oops, not too far. Excuse me. Oh God, no, I hope my computer hasn't crashed. Oh no. Sorry about that. Let me find the slide and then share the screen. Okay, so I won't bother to go into the display mode here. Yeah, so this material, yttrium, barium, copper oxide, if you change the concentration of oxygen, it turns out that this copper oxygen plane that's right here has exactly the right number of electrons so that there's one electron on each copper side. So by changing the oxygen density, you fill exactly one electron on each copper side. So that's the first thing. You've got to have some band, some atom which has one electron per site, which is unpaired. The second thing you have to do is to make sure that the Coulomb repulsion is large to keep two electrons from occupying the same site. And that's usually large when you have transition metals or copper or vanadium or something like that. So that's a typical situation for a mod insulator. It's one of these oxides or related compounds where you have some transition metal and some oxides, and then some other less vegetables like yttrium and barium, which are there to just adjust the density of electrons in just the right way. So it's a big art with chemical art to find exactly the right set of materials that will form a mod insulators. There's a huge library of them now. Some of them even have a triangular lattice with one electron per site on the transition metal, and there isn't any clear-cut example of the C2 spin liquid on the triangular lattice. They've another one with the Kagome where there's a reasonable evidence for the Z2 spin liquid. Okay, yeah, the other part of the question, how do you dope them? That's the difficult part, it's changing the oxygen. And often when you try to dope them, all kinds of other messy things happen in real life. And what's almost unique about the high temperature superconductor, they're also easy to dope relatively. Other mod insulators, many other mod insulators have been found, like strontium copper borate is another one, where doping is not so easy. And of course, but there's a huge effort around the world to doping more mod insulators in the hope of discovering even more interesting phenomena. Okay, so that was question number 1. Okay, sir, how many electrons be entangled to the same electron? Well, if you're talking about spin, only one. So yeah, there is something called monogamy of entanglement, which is, you can see that here. This electron in this particular state is entangled with that one. But as you move along, you have, so this pair of electrons here and this pair of electrons here, each has its own partners in this particular state. There's another state, let's look at these 4 here. So these 2 are entangled here. You can exchange partners, but each time it's a monogamous relationship. You have one partner to form that singlet, and then but you can exchange partners to form this more complicated state with longer range entanglement. So exactly how you build up entanglement is a very subtle thing. It's not free of constraints because of this simple fact here that once an electron is entangled with somebody, it can't entangle with anybody else. And this leads to very important theorems on the subadditivity of entanglement entropy and so on, which have been really crucial in many problems, both in condensed matter and in black hole physics. Does the mod insulator incorporate the theory of a mod transition, and if so, how? Not really. I mean, you can have the theory of the mod transition is a separate story that I haven't gone into. But step 1 is to understand the mod insulator. Then step 2 is to understand the phase transition from the mod insulator to the metal. And the nature of the mod insulator, the entanglement of the mod insulator, will influence the nature of the mod transition. And if you have continuous mod transitions, and there are some examples of that, then you can even get the scale invariant entanglement, some version of the scale invariant entanglement at the mod transition. But if it's a first order transition, as it often tends to be, then you don't get that. Another question, why can't molecules show entanglement? Well, in principle, they can. You can entangle anything. You can entangle a dead cat with a live cat in the famous Schrödinger cat, it's just much, much, much harder. So you could take a hydrogen molecule and entangle it with a different hydrogen molecule, in principle, by having them exchange electrons or something. It's very hard to do. I mean, that's kind of what you can think of this as a molecule. This is a molecule here, a molecule here. Of these are two hydrogen atoms, say, and then they're getting entangled. So they have two molecules being entangled. But okay, this is part of a big crystal, when the interactions are very different than molecule, and no atoms are actually moving, and the energy scale is just right. But can you entangle different molecules, say in a cold atom experiment? I don't think there's been much progress in that, but in principle it could be done. Can you please explain briefly the Boltzmann-Landau theory of quasi-particles? Okay, so I guess I mentioned this here. Well, okay, so there are two ingredients into it. One is the Landau theory of quasi-particles. And what that says is that when you have some excitation here, of course, this electron, when it's excited, will perturb all the electrons around it. But the theory of quasi-particles says is that there's a new particle which looks just like an electron, but it's the electron with its cloud of perturbations. Maybe there's some picture here. Here, the electron has a little cloud around it. Okay, so that whole object is called a quasi-electron, but it has charge E, has spin a half, and all the basic properties of an electron, except its mass may be slightly different. So that's the Landau theory of quasi-particles in a nutshell. And the earlier Boltzmann theory, where Boltzmann was just thinking in terms of classical particles, but amazingly, his theory was very easily generalized to quantum particles, is you take a distribution function of these quasi-particles, quantum quasi-particles, and you say, okay, at this point, this is the probability of finding this density of electrons with this momentum and this energy and so on. And then you write down an equation of motion for this distribution function, where the most important term is this collision term. Every time there's a collision, the electrons, the distribution function changes. And so that was written down by Boltzmann for a classical gas. I mean, Boltzmann died well before the introduction of quantum mechanics. But you can do the same thing for quantum particles, for quantum distribution functions, and you just replace the the collision between the electrons by the collision probability, which is just given by the scattering cross section, something you work out at the end of your quantum course normally. So just extending the Boltzmann ideas to quantum distribution function and quantum scattering, you get the quantum Boltzmann equation. And that's the basic workhorse tool for describing ordinary metals. Is the same entanglement concept used in the theory of Hawking radiation? Yeah, if so, exactly how does entanglement work in black holes? Great question, because I can now show my slides on this. Okay, so let me say a little bit about black holes. Let me see. Okay. So here's a black hole. It's a very dense object. This is the radius of it, given the mass m, and this mass is so large that anything inside here can never escape. Light cannot even come out of a black hole in Einstein's theory of relativity. So how does entanglement work? Well, you take your pair of electrons, which form an EPR pair, just like the valence bond. And now imagine a thought experiment where I separate them. But I put one inside the black hole and one outside the black hole. Okay, so now I remember I told you the idea of a quantum state has no locality associated with it. So if I do this carefully, the inside electron is inside the black hole is still entangled with the outside electron. Okay, so they form they still form an entangled state. But there's a problem here. If I'm outside the black hole, fortunately, and I have this electron with me, no one can ever tell me what's happened to the other electron. It's pointing down. So therefore, as far as I'm concerned, this electron is totally random because it's not correlated with any other information I can get about this electron, because that's behind the horizon. It's gone forever. So to me, this looks like a random electron. And a random electron, well, randomness is entropy. So that's the very simple explanation, that because of quantum entanglement between the inside and outside of a black hole, there's an entropy and a temperature. And these are the kind of arguments that Hawking and others use to show that black holes have an entropy and a temperature, and it's entirely due to entanglement. So one of the consequences, which is really remarkable, of this type of entropy-induced, entanglement-induced entropy, is unlike any other entropy, like the entropy of a cup of coffee. The entropy of a cup of coffee is proportional to its volume, how much liquid you have in there, and also depends on the temperature. Well, for a black hole, the entropy depends on temperature, but it's not proportional to volume, it's proportional to the surface area. And the reason is it's entirely an entanglement entropy. It's not an entropy due to some randomness because of unknown initial conditions. This could be a black hole at very, very low temperature. It still has an entropy because there's entanglement across the horizon. Okay, and so that's really and it turns out they also have this Planckian time relaxation, which makes up the connection to the Syk model. But the question was, entanglement related to Hawking radiation, right? So now the point is, and the whole question of monogamy of entanglement also comes up here. I said that, this other electron is lost forever, but not really. It's not really lost forever because Hawking told us that black holes radiate. So eventually, this electron will come out, or in the form of some radiation. So eventually, I can reconstruct the electron, the initial state of the black hole. But how you reconstruct it and how this is compatible with the monogamy of entanglement, because now this is telling me that, the late radiation is entangled with this electron, but I thought this electron is entangled with me before I put it in there. So how can it be entangled with both? And that's, in some sense, Hawking's information paradox, which has now been understood, I think, I would quite well, at least people tell me, by computations that people do using the Syk model and related models, where you can build in the analogs of evaporating black holes. Okay. Then how does quantum information play a role in phase transitions? Well, not directly, but you can certainly, the theories that we have of quantum phase transition are not directly expressed in terms of quantum information. But there are various quantum information diagnostics like entanglement entropy and various other Renyi entropies, and they give you very precise diagnostics of certain features of the quantum transition. Is there something limiting multi-particle entanglement systems you discussed, such as 3-electron entanglement in a state? I'm not sure I understand that. Yeah, I mean, I think I vaguely mentioned that there are constraints in entanglement, which are related to various constraints and theorems on additivity of entanglement entropy. But the zoo of possibilities, that's kind of what we work on, is trying to write down the different zoos of possibilities of entangled states in different materials is extremely large. So, in fact, the biggest problem is not finding the right entangled state, is figuring out which is the correct one to describe the experimental observation. Is entanglement limited to electrons only? Up to which scale we can see entanglement? No, it could be anything. In fact, the whole theory of quantum measurement is based on entanglement, because when you see something, you're entangled with what you saw. So everything, in some sense, is entangled with something else, but not in an interesting way that we can control. And as far as we know, there's no limit to it. I mean, there have been ideas that, including, I think Einstein was probably a subscriber to related ideas, that somehow entanglement is okay. It's all well and good when you're talking about two electrons. But eventually, when the system is large enough or big enough or far enough apart, something else has to come in, and the quantum theory has to be incomplete. But so far, there's no sign of that. Question you decide how large is enough. So people have been looking at bigger and bigger and bigger and bigger systems, and no one's ever seen a point where somehow quantum mechanics doesn't apply. Quantum mechanics makes the separation between the observer, at least the old formulation of it, between what's the microscopic system you're observing and the measurement apparatus. But you can change that boundary. You can move the boundary between what's being observed and what's doing the measurement. And as you keep moving that boundary and making the measurement apparatus part of your quantum system, you've never seen a problem to making it as big as possible. Okay, so I don't believe there is such a limit, but many other people do. So I'll leave it at that. All right. Okay, yeah. Those are great questions.
Yeah.
I don't think that.
Yeah. See, okay. I think there is any further questions? No, actually, can I ask one simple question? I mean, you said Syk model is related to emergent gravity.
Yeah.
I mean, is the space-time itself is emergent, or the gravity part is emergent in that?
It's the space that's emergent, not time. Yeah, there's an emergent space.
Model, so there's possibility there.
Yes. So basically, what happened, okay, maybe I'll show one or two slides on that. So yeah, so the basic idea is one of holography, which I mentioned here. So what you notice here about black holes is that they have the entropy proportional to surface area. So now people had this idea, which came out of string theory, that maybe there's a dual description of black holes in a theory which we call a hologram of a black hole, in a theory that doesn't have gravity. Now, if that theory doesn't have gravity, that theory must be in one lower dimension, because any theory without gravity, we know that the entropy is proportional to the volume, not the surface area. So there's this idea of that you can make a hologram of a quantum system with gravity and reduce the dimension by 1 and get a system without gravity. Okay, so there's dimensional reduction between quantum gravity and non-quantum gravity and the duality between them. And this was an idea that string theory has brought to fruition in many other contexts. So Syk is actually the far simpler version of it, where you can actually prove everything all the way through. And now Syk, as you can see, is a system with no space, really. Everything is moving everywhere else. It only has time. So there's only one space-time dimension. So if it's going to be a theory of gravity, it's going to be a theory of gravity in 2 space-time dimensions, 1 plus 1. So there should be 1 emergent space and 1 time. And you can show, and I don't have, of course, all the equations here to show you, but it can be done. And I'm just, in fact, writing a review article which will show every last step of it. There is a very important configuration where gravity looks 2-dimensional, and that's near the surface of a charged black hole. So when you're near a charged black hole, the transverse directions don't matter, and you only have 1 space dimension. So near the surface of a charged black hole, space-time is 2-dimensional. 1 space, the radial direction, and time. And it turns out that the theory of that, the near horizon theory of a charged black hole in our world, in using Einstein-Maxwell gravity, the theory of it in this region, which reduces your theory in 1 space and 1 time, because you can ignore this direction, is in fact the same as the theory of the Syk model. So that's kind of an amazing thing. And here are, some papers that have established this. Okay, that's the best I can do with just pictures.
Okay, thanks a lot, Professor, for a very wonderful talk, and Sure, all
Sure.
this really quite benefited by. Thank you.
Thank you very much.
Thanks
Yeah,
a
I mean,
lot.
if there's anybody who wants to speak up and ask a question, maybe I can take one or two more.
Yeah, if any
Okay.
other questions are there.
Okay. Yeah.
Okay.
All right. Thank you very much. And
Yeah, thank you.
okay.
Bye.
Bye.
Bye.